So, the example I have is example number 8 is that of the linear harmonic oscillator in 1D. Linear harmonic oscillator problem in 1D, one dimension. So, my H, the Hamiltonian given in this problem is the following. I straight away state the Hamiltonian, which I stated in the beginning of this lecture. P square plus omega square q square, and we need to find the extremal. We need to find the extremal, right? Okay. So, clearly the H is independent of the variable t, which is the independent variable. So, we look at the solution to reduced, Hamilton-Jacobi equation. Reduced Hamilton-Jacobi equation, which is nothing but, so the reduced Hamilton-Jacobi equation will be H is equal to a constant, where the variable p in H is replaced by del psi del q. So, I get the following. So, 2m times del psi del q square plus omega q whole square is equal to alpha, right. So, we have to solve this equation so to find psi. So, let me call this as my star. So, from star I see that my psi, the derivative of psi del q is square root of 2 m alpha minus omega q whole square, where alpha is positive, is a constant, right. And then the next step involves integrating this equation. So, psi of q bar comma alpha, well, it won't be q bar because this is a 1D problem. So, psi of q comma alpha is the integral of 2 m alpha minus omega q square dq plus the constant, which is the constant of integration. Now, we will see that when we are solving this class of solving the Hamilton-Jacobi equation for the conservative class, the number of constants typically equals the dimension of the problem, right. Even if we do not satisfy that, we can later on, when we find the solution, we can always club the constants so as to satisfy this constraint. The number of constants are equal to the dimension of the problem. Here we are solving the problem in 1D, right. So, in 1D we need only, so we need to define my solution only in terms of one arbitrary constant. So, this is without loss of generality, because even if we keep more constants later on in the solution, we can always club them to reduce the number of constants. So, that is why what we do is we take the constant of integration to be 0. So, constant of integration we take it equal to 0. So, this is 0 because we already have one constant sitting here, right. Okay. So, then we can I am going to directly write down the solution to this integral equation. We see that psi of q comma alpha is omega by 2 times q square root alpha square minus q square plus a square sine inverse q by a, right. And where my a is 2 m alpha divided by omega. So, my a is the following, right. And for extrema, I just need to solve one equation that I highlighted in my solution strategy. So, beta is del psi del alpha minus t, right. So, from here I see that this is minus m by omega sine inverse. I differentiate psi with respect to the constant alpha, and I am writing the answer directly. So, students should check all these steps which involves algebra. So, this comes out to be this minus t, or from here I can directly invert to get q as a function of t. So, from here my q as a function of t comes out to be negative square root 2 m alpha divided by omega sine omega by m times beta plus t, right. And the solution is similar to, recall that we had looked at this problem of geometric optics in more than one occasion. Especially we had seen the solution to this system in our previous lecture. So, recall I have the number example 3 in my lecture 13, the previous lecture series. Okay. So, that completes this example, and let us now look at how to solve. We have right now just shown the solution to this special class of Hamiltonian system, namely conservative system. The next set of discussion will be involving how to solve this Hamilton-Jacobi equation for this conservative system class, okay, for this conservative system. Namely, we are going to look at the method of separation of variables. So, the method of separation, which we promised few minutes back that I am going to talk about it. So, method of separation of variables for conservative system. Okay. So, let us look at this method in the most general form. So, consider the reduced Hamilton-Jacobi equation for the conservative class. Okay. So, consider the reduced equation. We see that this is also equal to h of q1 q2 qn comma del psi del q1 del psi del qn. This is also equal to, let me call the constant as E, the Hamiltonian equal to some constant, let us call it as E. So, or I am going to rewrite this by saying that this is equal to 0, right. Okay. Now, suppose we are in a situation where all the functions of q1, which is this one and this one, they can be clubbed together in the form of g of q1 comma del psi del q1. Suppose we are able to separate out one of the variables, that is q1, right, and write it in a specific form. Let us say the function to be g of that function, g of that variable. So, what I said is the following: suppose q1 comma del psi del q1 appears through a combination, of the form g1 of q1 comma del psi del q1, right. So, where g1 is a known function, So, g1 is a known function. So, now let me call this equation as 1. So, 1 now is identical to the following form. So, this is identical to f of, well, now this is a different, well, I must use the same function. So, this is h now, h of g1 of q1 comma del psi del q1, right, comma q2 to qn comma del psi del q2 comma del psi del qn minus E is equal to 0, right. So, now notice that since we have separated out the variable q1, possibly in this situation we can have a solution in which the variable q1 can be separated. So, which, if possible, so let me call this expression by 2, which if possible possible will have a solution of the form psi is equal to psi 1 of q1 comma q plus r1 comma the second function in which all the other variables can be clubbed, right. So, we have separated out the solution in which the variable q1 appears, right, where capital Q is the generalized coordinate, the coordinate in the new Hamiltonian system. Okay, so, and that can also appear here. Okay. So, I call this set of equation to be my 3. So, notice so what have we got here? So, notice that now since my variables q2 to qn have been separated out from q1, so then del psi del q2 will be nothing but del psi del r1, sorry, del r1 del q2 and so on so forth. So, if I were to use 3 in 2, then some of these derivatives can be simplified, right. So, using my expression 3 in 2, then I see that f of g1 of q1 comma del psi 1 del q1 comma g2 to gn. Now, the other derivatives del psi del q2 can now be simplified as del r1 del q2, because q2 to qn appears only in the function r1, which is the remainder function, okay. R1 to del qn, right, and we see that this is minus e, this is equal to 0, right. Okay. So, what have we got? So, notice that g1 is only a function of, this is a function of q1 only, right. So, assuming so this is my h, assuming g1 is, suppose I have found this function g1 such that this function g1 is differentiable with respect to q1. So, assuming g1 is differentiable with respect to q1, what we see that, let me call, so we differentiate, so let me call this as 3 prime. So, we differentiate 3 prime with respect to q1. I see the following, del partial h partial q1 is equal to partial h partial g1 times partial g1 partial q1, right. Okay. So, we see that del h del q1 is del h del g1 times del g1 del q1. Okay. So, this is equal to del e del q1, but e is a constant, we are going to get that this is equal to 0. Now, this equation tells us that either this is 0 or this is 0, but that this one cannot be 0, because we are, in other words, we are saying that an arbitrary function g1 is constant with respect to q1, and g1 is only a function of q1. So, which means the function g1 is essentially a constant, right. So, this is not possible, this is so this equal to 0 is not possible, because this implies that essentially our function g1 is a constant, that cannot be the case. So, which means that del h del g1 is equal to a constant, sorry, del h del g1 is equal to 0. So, which means the argument is exactly the opposite here. So, what have we got here is the following. that so either this is 0 or this is 0, but del H del G1 this cannot be 0, right, because otherwise and the answer to this reasoning is because G1 is arbitrary, it's an arbitrary so it's quite general. So this sort of separation is for a general function G1, right. We cannot all the time have that del H del G1 is 0, right. For certain class of functions G1 it may be the case, but not for all sorts of functions G1, right. So which means that del G1 del Q1 is equal to 0, or my G1 which was a function of Q1 comma psi of Q1 psi prime of Q1 comma capital Q, right, is purely a function of the generalized coordinate capital Q, right, because we have already eliminated out the dependence of Q1 on G1 through this argument, right. Okay. So we have now the following. So let me call this finding as my 4. So which means that this condition here, the condition 4 is actually a first order differential equation for my unknown psi 1, right. Psi 1 is the only function which depends on Q1. So from here I can find out my function psi 1, right. So similarly we can continue this process for psi 2, psi 3, psi 4 and psi n and so on. So similarly what I have is suppose Qk comma del psi del Qk appear Qk comma this appear in 1 as the functional form Gk of Qk comma del psi del Qk, right, and so they appear as the functional form Gk, where Gk's are all known from k2 to n for each of the cases, and from here I can deduce that psi of q bar comma q capital Q bar can be written in the form of psi 1. We are saying that we can continue our separation of variables to all the dimensions, to all the possible components of the dependent variable, right. Okay. So let me call this expression 5, and where my function psi k's they satisfy the psi k's satisfy n uncoupled first order differential equations, n uncoupled first order differential equations of the form Gk of Qk comma psi k prime of Qk comma Q bar equal to Ck of Q bar. In the along the similar fashion we will have the first order differential equation for each component, like we did it in the first component, right, where it turns out where Ck's are not independent. So Ck's, the constants, they satisfy our original Hamilton-Jacobi equation, they satisfy the reduced Hamilton-Jacobi equation. So they satisfy 2, right. So what is 2? So 2 is this quantity, right. So, instead of G case, I replace the G case by C case, right. So, they satisfy 2, which means that H of C1, C2, Cn minus E is equal to 0. Essentially, this equation is used to eliminate, one of the CIs, right. So, which means that CIs are not completely linearly independent of each other, but this is one linear dependence in which we can eliminate one of the constants. Okay. So far I have described the general methodology of the separation of variables for conservative systems. So, let me summarize. So, solution strategy using separation of variables, right, for conservative systems, right. So, let us say we assume the solution of the form. So, I am going to use my previous numbering, assume solution of the form 5, right. So, what is 5? Let us go back. So, assume solution of this form, right. So, this is what we have. So, assume solution of the form 5 and then identify the G case. Identify G case, the functional dependence of Qi's via 6, right. So, again going back. So, 6 is this quantity, this setup. Okay. So, going back now. So, once we have identified G case, we solve 6 for psi case, and substitute in our equation 5, right. We substitute in our equation 5 here to get our generating function psi, and which is what we are after, right, which is the solution of the reduced Hamilton-Jacobi. So, let us look at one example which involves this solution strategy, right. So, the example is numbered as 9 following our sequence. So, the example is we are solving the problem in Cartesian coordinates, right. We consider the motion of a particle. In space under the action of gravity, and the gravity only acts in one of the coordinates q3, right, q3 direction with Hamiltonian as follows. So, H is equal to 1 by 2m, which is given by P1 square plus P2 square plus and so on, plus P3 square. Well, there are only 3 components. So, P1, P2, P3, it's a problem in 3D. Okay. So, P1, P2, P3 plus so this is my kinetic energy plus the potential energy is given by mg q3, right. Okay. Where my mass is m, g is my gravitation constant, and q1, q2, q3 makes their own sense. Now, so we write down our reduced Hamilton-Jacobi equation. So, my reduced Hamilton-Jacobi equation is as follows. So, H of q bar comma p bar is equal to a constant. Let me call this as E, and then from here I replace p by del psi del q I, and from here I can, so I know the form of the Hamiltonian. So, I get the equation as follows. So, this is 1 by 2m. So, instead of P1 square, I have del psi del Q1 whole square. Instead of P2, I have del psi del Q2 whole square, and instead of P3, I have del psi del Q3 whole square plus 2m. Well, what have I got? Well, I have multiplied throughout by 2m. So, plus 2m square GQ3 plus this quantity is equal to so minus 2me, this is equal to 0, right. So, now I have to solve this system, we have to separate variables, or the first step involves identifying the functions gk's in which the variables q1, q2, q3 can be clubbed together. So, first of all, the step 1 involves assume a separable solution. So, assume psi is psi 1 of q1 comma q, right, and plus psi 2 of q2 comma q plus psi 3 of q3 comma q. So, assume a separable solution. The second stage is identifying gk's. So, note that I can take my gk g1 to be this. So, we can take gk to be del psi del qk for my first two components k equal to 1 and 2. Notice that they are quite similar, but for the third component I have q3 appearing, here and here. So, I have to take my gk to be this, right. So, I take my g3 to be del psi del q3 square plus 2m square g times q3, right. Note that I have not taken a square in g1 and g2, because even if I had taken a square, the solution involves gk set equal to the constant ck. So, we could have taken square roots. So, taking square does not matter in the first two components, right. Okay. So, then the third stage involves the solution to these equations to find psi k's, right. So, note that for k equal to 1 and 2, the solution methodology is identical, and we see that del psi k del qk is equal to a constant ck as a function of the generalized coordinate, or from here I see that psi k is ck of qk plus a constant kk of q, right. I have just integrated this. We see that the psi k's for k equal to 1 and 2, they are linear functions of the respective position coordinates q1 and q2. Okay, for the third case g3, for k equal to 3, I have that. So, what have I got? I have that del psi del q3, del psi del q3 is square root of c3 of q minus 2mg, well 2mg, well it is m square, the constant is m square, yes. So, 2m square g times q3. So, now I have to integrate this equation, and notice, so what I have to do is I have to find psi as a function of q3 comma q bar, which is integral of this expression. So, this is integral with respect to q3, but we can eliminate C3 with respect to, well, we can eliminate this third constant in terms of C1 and C2 using my H is equal to E, right, using that expression. So, we eliminate one of the constants, right. As I said, we have one constant H is equal to E. So H is a function now of C1, C2, C3, right. From here I get that my psi 3, my psi del, so psi 3 is the integral of this following quantity. This is 2me minus C1 square minus C2 square, these are all functions of capital Q, minus 2m square g of Q3, and then we integrate with respect to Q3. Now see that this integration is with respect to Q3, where Q3 appears only in one place. So this is far more simple than to well, this is almost similar, but we have eliminated one constant. Okay. So I am going to write down the answer. The answer to psi, so the answer psi 3 comes out to be the following: minus 1 by 3 m square g times square root, well, times the following quantity 2m, well, 2m square e, well, 2me minus C1 square minus C2 square minus 2m square g times Q3 to the power 3 by 2 plus another constant K3 of Q, right. Now notice, let me call this quantity inside the power 3 by 2 as gamma cube, where gamma is the square root of this quantity here, which is underlined, right. So finally my solution psi is psi 1 plus psi 2 plus psi 3, right, and these are nothing but C1 times Q1, C1 of Q bar plus C2 of Q bar times Q2 plus the third, in the third expression I have minus 3m square g of gamma cube plus k of Q bar, right. Now notice that so these two are my constants. These are my constants in the framework P bar comma Q bar. These are my constants in the original reference frame, and we also have a constant sitting here. Well, we also have a constant, not this constant, but we also have a constant sitting here. So this is also a constant which is inside gamma, right. And finally we are saying we are introducing another constant. So we have introduced 1, 2, 3, 4 constants. As I said previously, in an n dimensional constants we try to keep n, in an n dimensional problem we try to keep n constants. So we take k such that k is already absorbed in the third constant 2me. So we only have a 3 constant problem, right. So what have we done is we take our C1 to be alpha 1 and C2 to be alpha 2. These are my constants in my original reference frame, in small letter reference frame, and my E, this quantity is arbitrary and constant, so that I take my E to be alpha 3 and I take my k of Q to be 0, which means essentially I have absorbed one constant, right. So now my solution of the reduced Hamilton Jacobi looks like the following. This is alpha 1 Q1 plus alpha 2 Q2 plus well, minus 1 by 3 m square g times gamma, well, times 3 by 2 of, well, 3 by 2 of 2 m alpha 3 minus alpha 1 square minus alpha 2 square minus 2 m square g times Q3, right, to the power 3 by 2. So all it needs to see is whether the solution is complete or not, and only then we are able to find the extremal Q. So check that this setup del 2 psi del Q j del alpha k comes out to be this matrix 1 0 0 0 1 0 0 0 minus mg by gamma, where gamma cube is this expression, and I see that this is also equal to the determinant. So the determinant of this matrix is the determinant of this quantity, which is mg by gamma, and this is certainly not equal to 0 provided gamma is defined, right. So, psi is, so the conclusion is psi is complete, which means now we are able to find the extremal. The extremal is given by the solution to this following set of equations. I see that are given by beta k is negative del psi del alpha k for k equal to 1 and 2, and my beta 3 is minus del psi del alpha del alpha 3, and so this is my, this will give my extremal to the reduced Hamilton-Jacobi equation. Now, if we were to seek the extremal to the original Hamilton-Jacobi equation, extremal to the original equation, where suppose we want, so what is the relation between the original and the reduced? We had the dependence of t. So, here the solution to the original Hamilton-Jacobi will involve beta k del psi del alpha k, k from 1 to 2, but now beta 3 is equal to minus del psi del alpha 3 minus t, right. And from here I can find out that my extremals are such that qk is minus beta k. I am inverting this relation by plugging in psi. So, plus alpha k by m times beta 3 plus t, this is for k equal to 1 and 2, and q3 is equal to minus g t minus beta 3 square plus 2 by mg my alpha 3 minus 1 by 2 m square g alpha 1 square plus alpha 2 square, right. So, my original Hamilton-Jacobi is where the time, the independent variable appears. So, once we have the solution to the reduced Hamilton-Jacobi, we have shown that all we had to do was to change our last coordinate, where the nth coordinate as follows, right, and that from here we can get the extremals. So, this is my extremal solution, right. Okay.